So hello everyone, and welcome to this talk titled When They Go High, We Go Low. My name is Tal Zwick. I'm a developer at Metal Bear, where we develop MirrorD. And this talk is about solving a seemingly high-level problem, the problem of cloud-native developer experience using very low-level techniques. More specifically, we will discuss MirrorD, which is a dev tool written in Rust, open source, and it's for cloud-native applications, so for the development process of cloud-native applications. And MirrorD enables cluster-connected but local execution of those applications. And what that means and what it looks like will become more clear as we proceed. So, as I said, the high-level challenge that MirrorD addresses is the challenge of cloud-native developer experience, and more specifically, just being able to run your code while developing them. And the solution MirrorD employs is at the operating system process level, which is maybe a bit unusual for the cloud-native space. So first, we're going to talk about what MirrorD is for. And once that is out of the way, we're going to take a look at some of the low-level technical details of how MirrorD works. And then to wrap it all up, there will be a short live demo of MirrorD. So first, what MirrorD is for. Running the code you're working on is important and helpful while writing software. And with many types of software, that's an easy enough task. But with cloud-native application, it becomes not so trivial at all. And I think we shouldn't abandon useful development practices because they are hard to implement for cloud-native applications. We should just develop the tooling to make them easy. But how do you run your cloud-native application while developing when the application, for example, accesses files that only exist inside the Kubernetes cluster, or when it uses other services in the cluster over IP, or when you need other services to generate requests to that application in order to test it meaningfully? And besides, running your code often is good, and you might not want to spend time containerizing and deploying your application after every little code change that you want to test out. So there are multiple approaches to solving this problem, and they don't all offer the same capabilities and don't result in the same workflow for the developer. But there is, for example, remote debugging in the cloud. Some teams try to run everything locally, the whole application or the whole system. But the approach MirrorD takes is to enable local development with remote access. There are also other tools like telepresence or Jafira that also belong to the remocal category. But MirrorD works on the process level, not on the machine or container level, which results in a slightly different workflow and also results in some nice technical talk material. And the idea is to have the optimal development experience for running the code. And for us, that means make it as simple as running non-cloud native code. So basically, just a click on the run button in the IDE or a very simple CLI invocation. And at the same time, we want also developers to be able to run with meaningful data and realistic conditions. And also, we want them to be able to utilize existing environments and not require additional resources. So with MirrorD, developers can execute their code locally, either in a shell or in their IDE. And when the application accesses resources from the cluster, it gets the actual traffic and data from the cluster, even though it's running directly on the developer's computer. And developers can run their code very easily and do things like stepping through breakpoints in their IDE, but still take advantage of the realistic cloud environments that they already maintain in their team, all the while being non-intrusive and not actually changing what is currently deployed to the cluster. Because MirrorD lets the software run in a simple process on the developer's machine and just adds a thin layer of transparent virtualization for connecting the application's I/O to the cluster. And the way Mirror achieves that magical effect is by injecting a dynamic library into the application's local process and hijacking some key operations made by the application. So this leads us to the next part, the cool technical details. And here we'll take a look at the key steps Mirror takes in order to hijack an application's calls and make them magically succeed even when trying to access resources that don't exist on the local system, but do exist inside the Kubernetes cluster the developer is working with. So the first thing we need to do in order to get our code into the process's memory, in order to hijack those calls is to get our code into the process's memory. And the way we do it is when a user tells mirrord to execute a program, mirrord executes that program, but first asks the dynamic linker to also load our dynamic library into the new process's memory. You might know it as the LD preload trick on Linux. On macOS, that same environment variable is called dyld insert libraries, and mirrord just adds the path of its own dynamic library to that environment variable, and the dynamic linker loads our code, mirrord's code, into the new process in addition to that process's code. Okay, so now our code is in there, but we still need to run it. Just having our code inside the process's memory doesn't mean it runs. Of course, the user application doesn't call our code, doesn't execute it, because it isn't and shouldn't be aware of mirrord. So in order to ensure code runs, we use another feature that dynamic linkers offer, and that is what is sometimes called a constructor. And that is basically just code that is placed in a specific section of the binary. And this code will be executed on start time of the process, or when it's loaded. And as mentioned before, mirrord is written in Rust, so that's the syntax we can see right here on the screen. And there is a Rust package that offers an attribute macro that makes defining a constructor very easy for us. So we just have to add this little ctor attribute above a function, and that function will be, the code inside that function will be executed on startup. So yeah, this is how we get the code that we got into the memory to actually run. Yeah, but before that, so now we have basically code execution inside the user's process, right? Because we can insert code and we can make it run. So the next question is, what do we run? But before we answer that question, just a quick recap so that we're all on the same page. Quick introduction to Libc. So Libc is the C standard library. It implements useful low-level operations. It's used indirectly by almost every programming language. So when writing some high-level code or like some higher-level language code, of course, developers don't actually write the calls to Libc themselves. They usually use the standard library of that language that in turn calls the Libc, or some built-in operations or whatever. But basically, at the end, the compiled binary or the interpreted program will result in calls to the Libc library. And that means that code that is generated by most languages, I mean binary code, won't directly include any syscalls. It will usually only include calls to Libc, and Libc in turn is the one to call syscalls. OK, so now that we have code execution inside the user's process, what we do run on startup is code that utilizes Frida in order to hook Libc functions. Frida is a dynamic instrumentation toolkit, and it lets us manipulate the process's code while running. And so we use it to hook some Libc functions. And in this context, hooking means that whenever there is a call to that Libc function, instead of that Libc function, our own code is being executed. And the way it works is Frida replaces the first couple of binary instructions of that Libc function with the jump to our code. And so for each Libc function that we want to hook, we define our own Rust function with an identical signature. This is why we also need to use Rust's FFI features and make sure that we have the C ABI and C calling conventions for those functions. And of course, the code that we put inside those functions is not the code that is executed on startup, right? The code that is executed on startup just makes sure those, like the Libc functions, are hooked and result in calls to those functions, to our detours. But those detours are actually only executed while the user's application makes calls to those Libc functions. OK, so the next question is, what do we do inside such a detour? And the answer is, first, we check the configuration or flags that the user provided mirrord. And then we decide if this specific operation, if this specific Libc call should happen normally, as if running without mirrord, or in the cloud. So everything can be fine-tuned. Users can choose to read some files locally and some files in the cluster, or read in the cluster and write locally, or whatever they want. And if we decide that the operation should be carried out in the cloud, mirrord sends the operation to a mirrord agent running in the cloud. That mirrord agent is spawned just in time on the start of the session and is deleted at the end. That agent carries out the operation, like, for example, reading a file or connecting to a socket inside the cloud, and it then sends the result back to mirrord on the developer's machine. So, for example, for reading some bytes from a file, the application makes a call to Libc. We then hijack that call. We send it to the agent. The agent reads those bytes inside the cluster, sends the read bytes back to mirrord. Mirrord populates the application's buffer with those bytes and returns from the call. The application gets a success code, can read the byte, and is happy, and doesn't even know that anything special happened. So it kind of just thinks the application, like we kind of fool the application to feel like it actually is running inside the cluster. So at this point, you might be wondering how we access the deployed application's data, its file system, traffic, environment variables, etc. So first, we need to know where to get the data from. And for that, users can specify a target for mirrord, which is either a pod, a deployment, an Argo rollout. I think we now also support jobs, maybe cron jobs, and that kind of stuff. So the most common use case for mirrord in general is working on a new version of some existing microservice. So typically, or users would use that resource in the cluster as the target for the run, because that's the resource that has all of those data and traffic that our local application needs. So then the Mirror-D agent runs in a pod on the same node as the target's pod. It joins the application's Linux namespaces. So be aware, this is not the same as Kubernetes namespaces, just a name collision. The Kubernetes namespace is actually, it doesn't actually matter for any of this. And yeah, in order to access file system, we basically just access it over the relative path to the container's root path. So to summarize, the agent runs in a container on a pod on the same node as the target. So at the end, it's just two processes on the same Linux machine. So that's at least the cool DIY way for us to do it. But ever since there is the Kubernetes introduced ephemeral containers, we can also just use an ephemeral container to run our agent, because as ephemeral containers are designed to debug running pods, they have access to all of those resources by default. So Mirror-D lets users choose if they want to have the agent in a separate pod or in an ephemeral container. And I think we'll probably move to make that the default at some point. OK, so when we talk about resources the application can access from the cluster, the main ones are network traffic, both starting connections and accepting incoming connections, and also DNS resolution. And then there is file system access, and environment variables. So just to zoom out a bit, we see that the main components are the Mirror-D binary installed on the developer's computer, and the dynamic library it injects into applications they run with Mirror-D. And in the cluster, there is the Mirror-D agent. Now, the dynamic library forwards operations to the agent, and the agent sends data from the cluster to the dynamic library that makes it available to the user's application, as if that application is actually running inside the cluster. OK, now after we went on this little journey through some of the technicalities of how Mirror-D works, let's look at what users see when they use it. So for that, I'll switch to the demo. 1 second. OK, so right now we're in an IDE in Goland, and yeah, actually, I have a slide for that. So we'll show that first, just so that you can. Yeah, OK. So for that, we have this little example setup with some custom microservices written in Go. And together with a Redis and Kafka service, all deployed on our cluster. And we'll step through a scenario of a developer working on the IP visit counter services. OK, so now I'll go back to the IDE so that we can see what it looks like. OK, so here we're in a Golang IDE. I already have the Mirror-D plugin installed and enabled. And I have a basic, a very basic Mirror-D configuration that generally, basically only defines the target, so that I don't have to choose it in a dialog. And here we have this very simple Go web application. So we have some auxiliary functions to set up the connection with Redis, with Kafka, to load the configuration, and get count is the function that handles incoming requests. OK, so now I'll just start debugging that application. And OK, we hit the first breaking point. I'll step in and see what it does. OK, so that we can see that this little function loads and populates configuration fields from environment variables. And the nice thing is that those environment variables don't exist on my system. But nevertheless, if we jump forward, we can see right here that the application actually gets values from those environment variables. And now we know that the reason that works, even though I don't have those environment variables on my system, is that MirrorD fetched those environment variables from the cluster and made them kind of transparently available to the application. OK, step out and continue. So now we can see that the next thing this application does is to make a file access, so read a file using a path it got from this configuration. So let's see, it's going to read config.response file, and that's /app/response.txt. Now, of course, if I go over to my terminal and try to read /app/response.txt, it's not going to work because I don't have that file on my system. But once I go back to debug and step forward, the operation is successful and the application actually got some bytes. And once again, the reason is because MirrorD hijacked that operation and carried it out inside the cluster where this file actually does exist. OK, next thing on the agenda is setting up the connection with Redis. So if we step in, we can see that it again uses an address that it got from this environment variable, and it's Redis main with a port. Of course, if I try to just connect to that host from and host and port from my system, curl is going to tell me it can't even resolve this host, so it can't even get the host, like the DNS resolution for this name, and that's like obvious because it's some this name is like internal inside the cluster, right? It's not just visible on my local network. But once again, Redis is going to be able to resolve that host name and also create a connection. And the reason is because both operations, so DNS resolution and the outgoing connection, are both actually carried out inside the cluster. OK, stepping out. Next thing is setting up Kafka. That's quite similar, so I'm just going to skip forward. And then we define those two routes, one for health checks and one for the important function this application does. So I'm just going to let it start listening for applications. We go into the console. We can see it already started receiving health checks from inside the cluster. Now, currently, I'm running in the default mode of MirrorD, which is mirroring mode. And in this mode, I'm not actually stealing away the application from I'm not stealing away the traffic from the application that is running in the cluster. So this means that the application that is running in the cluster is getting those health checks and is answering them. And my local application is receiving a copy. I could also, I think we still have 5 minutes, so. I could also run MirrorD in steal mode, where my application would be stealing all the traffic away from the deployed application. And I could also filter the traffic so that my application gets some requests, for example, the non-health check ones, and the deployed application gets the health checks and answers them. OK, so let's go over to the terminal. Just generate a request to the remote cluster, and we can see that our local breakpoint is hit, even though this request obviously didn't directly go to my local application, but to the cluster first. And now I can basically step through my code and see how my local application, if I want with some changes I can make locally, handles actual requests that reach the cluster. OK, I'm going to continue. Yeah, so those are some very basic features of Mirror-D, and this is basically what all we saw earlier boils down to. This is what it looks like from the user's perspective. OK, so that was a quick tour through the internals of Mirror-D. Mirror-D has a lot more interesting implementation details and cool features that I didn't have time to show you today. So if you're interested, you're welcome to read more on our website and look at our code on GitHub. And now that you've seen how easy it is to just use and just like start playing with, I hope you'll try it out and let me know what you think. I do recommend joining our Discord for live Mirror-D support from the community and also from the team, and also just to chat with us. And if you have any questions or want to talk to me, please feel free to just come say hi after the talk. I think we have 3 minutes for questions right now. So thank you very much for your attention. Thank you very much for the organizers. And I think we can have a couple of questions. I think, oh yeah, sorry, we have a microphone apparently, yeah.
Yeah, thanks for the talk. So Go builds static binaries by default right now. So how did you do that actually?
Sorry?
I think Go builds static binaries, so no dynamic linking involved. So, but your demo showed a Go binary, so how did you do that?
So I think it doesn't always do it by default. So for example, I think my application uses oh, OK. First of all, actually, I'm on macOS, and macOS doesn't per se have like those static binaries that's the same as that Go produces on Linux. So basically, on macOS, I think it will always work. On Linux, I think this would also work once you use. So I think the networking or like the web framework makes my application also use CGO, and that also results in a dynamic library. So I think most application would result, or most applications that can benefit from Mirror-D would result in a dynamic library, a dynamic binary anyway. And if they don't, you can just force a dynamic build.
Okay, and as a follow-up, so do you have any plans to extend support to also like be able to wrap static binaries? Like you could pull out all of this functionality that the LD preload does right now into like a sandbox or something, right?
Yeah, maybe. I think I don't know if any plans like that for now. I mean, you can always just open an issue on GitHub, and if it's popular, it will probably get implemented at some point. But, yeah.
Okay, thanks.
Thanks. I think there was a question here.
It was the same question.
Oh, OK. We're good. Any other questions?
Okay.
And I think this will be probably the last question, as we don't have any more time. But feel free to just come talk to me after the talk outside.
Quick question here. So when you showed connecting from the IDE to a pod that is running on a cluster, right? Do you connect to the pod itself, or do you connect to the containers running inside the pod? How do you map the connection?
Oh, yeah. So you can either specify which container you want to target inside the pod. Okay. And if you don't specify it, we're going to pick one for you. with some default logic of we try to guess which pod is the right one. But if you actually have multiple containers running and it's not obvious, you can always just specify that in the configuration, and that will target that specific container.
Have you tried with any sidecars?
No.
Running multiple. Okay, that would be great.
No.
Try.
Okay. Okay, so thank you very much. And yeah, if there are any other questions or you want to chat, let's talk outside.